not store it in a register. We'll just say, okay, this group is a register, a group of qubits, okay? So I would say this is just a collection of qubits. That is what very often what people refer to when say a quantum register. But of course, as the field grows, maybe later they will call this really a memory. But at this moment, we don't call it, right? Don't worry about that. So, for example, for 4 qubits case, right? We know very well it represents the tensor product of 4 C2 space, right? And what space is this? 16. I'm fishing for this, right? C16, right? Or we can say that this is a C2 to the power 4 space. We know that already. Now in this space, we have the basis states. What are the basis states of this state? What are the basis states of them? Okay, all of them. And what are they? 0, 0, 0, 0. 0, 0, 0, 1. Thank you. 0, 0, 1, 0. 1, 1, 1, 1, right? So particularly, I would like you to recognize that this one is 0, tensor product 0, tensor product 0, tensor product 0. Okay, you can treat that it is the tensor product of the basis states of each of the individual qubit. And then it becomes the basis states of this larger space. This one is tensor product 1, or 1. Right? And then as I said, if I know I'm doing decimal, this time I put 10 here. I don't need to if we are sure that what it means. Then I have 16 basis states. Is that okay? And it's up to you. You can call it A, B, C, D also. 16 alphabet, no problem. Right? But you need to recognize there are 16 basis states. So their broad version of what? What are their broad version? Well, just 0, 0, 0. 0, 0, 0, 1, and all the way to 1, 1, 1, 1. Okay? Do you agree? Right, so now although it's just quantum register, but basically say that now we're grouping more qubits together in form a larger space. And that's it, nothing special. It's just that I put a 4 qubit in front of you, it has a larger space. You don't need to do anything, right? So in general, if I have n qubits, right, the basis states are what? We talked about that already. They are from 0, 1, 2, all the way to what? 2 to the power n minus 1. Now, another way to write it is this. I can write all these basis states in a binary, right? I can write it in binary. But this 2 to the power n minus 1, I can also write it as a n minus 1, a 2 to the power n minus 1 plus an minus 2 to the n minus 1 plus all the way to a0 to the power 0. That is just how we write the transform a binary digit into a decimal digit, right? This one I know is confusing, but let's take a look at this example. 101. This is in binary. It is equal to what? 1 times 2 to the power 2 plus 0 times 2 to the power 1 plus 1 times 2 to the power 0 in decimal. Is that okay? So what is this? 4 plus 0 plus 1 equals to 5. Okay, that is the meaning of binary number, right? You have 4 of them. Why this is 15? Because this one represents 8, this represents 4, this represents 2, this represents 1. So that's why I'm saying the general N-qubit basis state can be written as this. And this AN1, AN2, all the way to A0 are just this 1, 0, 1, 0. Okay, just want to remind you about this. Yeah.
The second term.
Yes. Thank you. Thank you. Yeah, thanks for pointing this out. Otherwise, when you study, it will be super confusing. Yeah. From broad to cat, but this is just the name of the cat, right? Of the basis, right? And also, cat to broad is cat to broad directly. There's no complex conjugate. And basically, here is saying that this is the image of myself. I don't need to do anything because this is indeed the image of myself, right? But then if you say, I want to stretch myself in the real world, then what is the image of this one? Is the image of myself times the stretching complex conjugate of the image. Then you need complex conjugate. What I'm saying is if you 2i times this one, then broad version is 2 minus 2i times its broad version, right? So this one doesn't have any complex conjugate or whatever. Just a name, right? That's why it's very important to recognize here has no representation. It's only just a name. Good. Now, then I want to ask you, the basis has to be orthogonal, right? The base has to be orthogonal. So then what does it mean? It means UV equals to delta UV. Okay? They need to be the same. But not just this. The point is that every bit has to be the same. For example, what is the inner product of 8 and 9? I hope that you won't feel very confused now when I say inner product between 8 and 9. What does it mean? The 8th basis and the 9th basis inner product. What? Assume you don't know, right? I have not taught you that they need to be the same. Then how do we calculate? What is 8 in binary? What is 8 in binary? 1, 0, 0, 0. What is 9 in binary? Excellent. 1, 0, 0, 1. I still cannot see it, but do not forget 1, 0, 0 means 1, tensor product 0. Tensor product 0, tensor product 0. That is 1, 0, 0, 0, right? And then you try to do an inner product with it on 9, then what do you have? Now I'm going to group this together. This becomes 1, tensor product 0, tensor product 0, tensor product 1. Is that okay? Now, this is very important. Life is very easy, actually, in quantum computing. With this, sorry, I need to go here. With this, you only do the inner product individually. Remember what we learned about the Hilbert space earlier? You do the tensor product in the higher dimension. Is the same as you do, not tensor. You do the inner product in the higher dimension is the same as you doing them individually in the subspace. Right? Remember that equation? So this is equals to, but now I'm going to make this clear, right? I call this the first A, B, C, D. A, B, C, D. You don't need this, but I just want to make it clear. This is equal to what? A times 0, 0, B times 0, 0, C times what? 0, 1, D. Is this okay? Because I'm just doing the inner product in each subspace, the A space, B space, C space, D space. You cannot swap that. It's up to you how to write it. I have 4 electrons in front of me. You can come from left to right or right to left, or you can jump over. It's up to you. You always need to follow what you set up at the beginning. What is this? Evaluate it. What is this? Okay, doesn't allow me to. 1 multiply. What is the second term? 1 multiply. 1 multiply. 0. What is that? 0, right? So as long as you 1 qubit that is different, 1 qubit value that is different, then it is not the same basis vector, which makes sense, right? But I just want to highlight this, how you might not use this much in the class, but in the future when you see complicated algorithm, in order to write the equation, you need to recognize that each cat state can be represented as this equation, because it's just a string of binary number, and they equal to the decimal through this equation. Okay? Yeah, any questions? Say again? No, that's not a gate. You can say this is like an operation. You need all of them to be 1 in order to be 1, but that is not a gate. The logic is the same. Not about circuit logic. I'm talking about the philosophical logic. Right? Yeah.
So the 0 answer makes sense because they're orthogonal.
Yes, certainly. I just want to show you that it makes sense. No. They are orthogonal. They are orthogonal. I forgot to say actually orthonormal. Also, they need to be normalized.
So the inner product,
same thing, it should be 1. Yes, because every digit are the same, then it means you're doing 8, 9, 9. Right? They're exactly the same basis. Oh, good. Okay. Now, let's take a look. If I have an N-bit register, what is the general value? We talked about this in the very beginning already, right? But we still just need to put it in an equation more formally. But can you tell me what is the N-bit register? General value, quantum register, of course, right? We already know that classical or general value is the basis state, right? But for quantum register, what can it be? What is the keyword? Besides, I can store 0, 0 all the way to the power n minus 1. What else can I store as a quantum register? Well, superposition, linear combination of the basis states, right? So you can store from x equal to 0 all the way to 2 to the power n minus 1 of x, complex coefficient x. And this is just what I put in the previous slide. I just because I did not put in the previous slide, sorry, I did not, right? So this means what? C0, 0 plus C1, 1 plus C2, 2 plus all the way to what? 2 to the power n minus 1, 2 to the power n minus, I'm wrong, right? Where should I put the minus 1? Should be and I'm wrong, right? Someone say it should be C, right? This should be a index, right? C to the power n minus 1. Now, does it make sense? Okay. So remember in the first class, I said if you have 300 qubits, how many coefficients do you have? To the power 300, right? Because you have 2 to the power 300 states. So that's why quantum computing is so powerful. And what is the condition for this one to be used in quantum mechanics or in quantum computing? Very good. It has to be normalized. How do you write it in an equation? What does it mean to be normalized? The sum of the magnitude of the vector of the square of the magnitude of vector need to be 1. The whole thing equals to 1. Okay? Now, quantum computing is the same. No, I cannot say that. 1 qubit is easy, but multiple qubit, you will grow up, the space grow up very quickly. You still need to satisfy this one. Okay? So, then while there's some, I don't know, I give you an example to make it easy. For example, n equal to 2, then psi can be, just an example, summation x. I hope you try to play with this summation more. It is confusing. Do you agree? N becomes 2, right? And then it becomes what? Cx x, right? So it means this is C0, 0 plus C1, 1 plus C2, 2 plus C3, 3. Just someone remind me again, what is the meaning of 3 in the cat? Just the name. Yeah, so it's 2 qubit. It represent what? Which basis? 1, 1. Thank you. Yeah, that's so simple. Just thank you. Right? Remember what you are writing, right? So for example, it can be what? Equals to 0.5 I plus 0.5 no, 0.5 I plus 0.5 2 plus 0.53. Why it is 0.5? You have to square the amplitude. So someone asked me about an example. I put 0.5 in the first class. Did I pick that randomly? I pick it randomly, but it's subjected to this constraint, right? We do have 0.5 I squared plus 0.5 I squared plus 0.5 square plus 0.5 square equals to 1. It is normalized. Okay? Any questions? Say again?
What happened to the
What happened to the I? You tell me. What is I? What is I?
Oh, my.
Square root minus 1. And then what is magnitude? Magnitude, right? 1, right? Or you can say this. I mean, it doesn't hurt to really keep visiting the basics. I square is nothing but just I times I star, right? So I times I star is what? I times, what is I star? Negative I, right? Because it's I, right? Complex conjugate. So what is I square? Negative 1, right? Right? So I, of course, correct. The I's magnitude is 1. Its square is 1. Okay? Okay, so I want to show the data processing, but you know that already, but I want to show you again why it's so important. Now, as I said many times, the unitary transformation, right? Wait, actually I forgot why I want to say this statement. Right, but ignore it for now. Basically, is that now I have this psi. Basically, data process is apply the gate to the vector and let it rotate in the hyperspace, and we apply the unitary transformation to it, right? And different value of the register, maybe I should not say that, different bases, right? Different bases. You have different basis vector presented simultaneously due to what? Due to what? Why have different basis vector presented simultaneously? Due to superposition, right? So for any quantum register, I have, again, write it again, psi equal to summation x equal to 0 to 2 to the power n minus 1 cx x, right? So I have all this together, right? So if I have n qubits, then this is a 2 to the power n dimensional space, 2 to the power n d. Okay? Now, for example, how do I process it? If I can apply, if I have something like psi equal to like what we had earlier, 0.51 plus 0.5, I mean 0.50, 0.51 plus 0.5, 2 plus 0.53. If I apply a function to this one, in principle, due to the superposition, I get all of them at the same time. Is that okay? So just one computation. So this one we talked about that already, if you remember in the first lecture, right? That's why you achieve the quantum parallelism. So actually this you already know, you see, along the way since the first class until now, you already understand the power of quantum computing. You know how it applies this parallelism. You know it is a rotation of vector in the hyperspace. Here I just summarize what you already know. Okay? So we're kind of done with all the basics. You have all the tools. And now let's start doing something really quantum computing, right? Quantum entanglement. is something that people might not call it algorithm, but we can treat it as an algorithm. Yeah. I'm not saying apply a function. I just said I apply a function. This function contains a series of rotation, right? So that is a function. And this function is trying to rotate this vector. And at the same time, it's just actually rotating all these basis vector at the same time. And if this rotation of the basis vector, each of them are important to you, then it means that you are doing the computation all at the same time. Yeah. Of course, at this moment, you find this is meaningless, right? But later, the smart people come up with the algorithm and we will learn how we achieve that.